I don't know. I don't think you can. No, you can't record. No.
Okay.
But it will be available on the website at some point.
Okay, brilliant. Thank you.
That's not because we've got any objection to you filming your own, I think, Simon, is it?
No, you just can't technically do it from. I don't think you can do it from a. You have to.
If
do
you're doing it, I can't. Okay,
Yeah.
that's fine. That's fine.
Right. Can I just start the evening by saying Happy New Year to all our members and guests. And this is our first event of 2022. We still don't know when we're going to go back to face-to-face meetings, but the way things are going, perhaps that won't be too far distant. Tonight, I'd like to welcome Professor Richard Patrick as our guest speaker. He's going to talk about the biography of a hill, Grinlow, and the prehistory and geology thereof. Richard has been a resident of Buxton almost as long as I have, come in here in 1991, I think he said. And I nearly said you're retired, Richard. Is that correct?
I am retired. Thank you.
You're a retired professor from Manchester University and a fond dog walker in our woodlands. So without more ado, can I welcome you? And I'm sure you've got an interesting talk for us. And I know that you've got a question for our audience on a point of identifying some trees in the top of Grinlow.
I'll make
Okay.
make the audience work at the end. Yep. Well, good evening, everybody. Yes, my talk is on the geological history of Grinlow, and it deals with the time when the rocks beneath Grinlow were formed, right up until man came and messed around with the hill. So this is a geological map of the center of the UK, and we are where that red star is, on the edge of this blue outcrop of limestone of Carboniferous age, and the Derbyshire Dome. It's surrounded by other Carboniferous rocks. And certainly quite a lot of the talk, we will be focusing in on those rocks because those are the ones we can find at the surface. And if we look at a geological map of Grinlow, it's here on this blue, which is the limestone. There are some pinks, which are lavas, basalt lavas. And to the west of us, as we look out towards Burbage Edge, there are sandstones, mudstones, and coals. And these are all of Carboniferous age, 350 to 310 million years old. But these are just a thin skin. And what is beneath these rocks? Where was Grinlow before this lot were produced? And that's where I want to start the talk. We won't dwell too long on that prehistory, but I want to take you back to 600 million years ago. Where was Grinlow? Well, actually, Grinlow was here, very close to the South Pole. This is in the end of the Precambrian, and it was on the rocks which were formed beneath what the Grinlow Hill now were forming on a little tectonic plate called Avalonia, not far north of the North Pole, South Pole rather. And this plate makes its way northwards, really, for the next 600 million years, up to a position up here, which is where we are today. And if you want to look at the rocks which were forming down on Avalonia 600 million years ago, they are exposed, but not on Grinlow. You can go to somewhere like the Mendip Hill, not the Mendip, the Malvern Hills, the Malvern Hills. Here, the Malvern Hills, and a couple of faults have brought up Precambrian rocks formed down there by the South Pole 600 million years ago. These are the kind of rocks which are beneath our feet on Grinlow. Now, move forward 150 million years, Avalonia, which is, say, proto-Grinlow, if you like, is headed a little bit further north, and it's a plate, quite a small plate, and it's about to collide into two other plates, this plate of Baltica and Laurentia, and this ocean, the Iapetus Ocean, between those plates gets closed with subduction and mountain building. And if we just take a little zoom in, you can see on Avalonia is where southern Britain is. There's Wales, there's England, and up on this plate, Laurentia, is Scotland. And over the next 100 million years, these plates all converge to make one big continent, and England and Scotland become joined. Behind Avalonia, as it's heading northwards, is another ocean, which it too gets closed about 100 million years later. If you want to see the rocks which are forming here beneath Grinlow at this time, they're mostly mudstones and sandstones, a few volcanics, and the best place to go to them is pop over to Wales, in Snowdonia, the slate quarries, and Snowdon itself, old volcanic rocks. Those are the rocks which you find beneath us in Grinlow. And how do we know this? Well, if you do a cross section through Grinlow from Goyt, you go through the upper Carboniferous rocks, you can see the blue limestones here, the lower limestones here in green, and a borehole only 4 miles from where I'm sitting here near the cavern was drilled down from Woodale, and sure enough, it encountered those Precambrian and those Ordovician rocks beneath the limestone at only 300 meters below where we are. So what we look at actually on Grinlow is a thin skin, and beneath there is this old continent of Avalonia. Now, by the Devonian, the Iapetus Ocean has closed. England and Scotland are united. Here we are. There's this new ocean behind them. Grinlow is there to the north with the giant Caledonian Mountains. And Grinlow is part of a continent. And conditions in the Devonian were pretty dry. There wasn't much life on land. Plants had arrived, a few amphibious animals, some volcanism related to the mountain building, but it was a fairly dry area. And if you can see here, again, we've moved north and we're heading towards the equator. Then at last to the Carboniferous. So by the time the Carboniferous, about 340 million years ago, there's Grinlow is here. Now it's got very near the equator, still going north. And if you look at Britain, it's this area here, and zooming in, what's happened is a nice seaway has come in over southern Britain, most of Britain, a nice tropical sea. And the crust, which has been squeezed and crunched in the removal of the Iapetus Ocean, is beginning to relax a bit. And it's allowing this sea in, and it's quite quiescent period in the beginning of the Carboniferous. If you looked at the paleogeography of Grinlow 340 million years ago, what you've got is this light blue, which is nice shallow seas, and Grinlow is on the edge of one of these platforms of nice tropical shallow seas. There were some basins around, and there were also some little upland areas. And further north, beyond, up in Scotland, a big mountain chain, and actually to the south, developing a new mountain chain, but between a fairly quiescent period, and we of course are now near the equator. So Grinlow, as the rocks we see it, would have looked something like this. In fact, this is the Bahamas, and difficult to envisage here in January, but it would be something like this, a nice clear tropical sea, probably actually not much land. There's not much evidence that in the Grinlow area there was land at this time. So the view you would have seen if you'd stood on Grinlow near the temple in 340 million years ago would have been more like this. A lovely clear blue sea, probably 25 to 30 degrees centigrade. No land to be seen, but beneath the surface, an enormous amount of life. There will be sharks, early sharks swimming around, orthocones, and on the seafloor, lots of corals, lots of crinoids, a few trilobites, and a few shell creatures, brachiopods, full of life in this clear blue sea. Now, the result of all that clear blue sea, anybody who's knows Grinlow at all, is the grey limestones we see up by the temple today. And this is called the Below limestone, a thick unit of limestone, which forms the whole of the hill. If you look at the limestone, there's not much to show what life there was in terms of macro fossils. It's grey. I don't want to call the word boring to any rock, but yeah, it's a fairly boring rock. It's got a nice lot of weathering features in it, but no macro fossils. And in fact, the Below limestone itself is generally not good for large scale fossils. However, if you look closely, there are macro fossils on Grinlow, and this is the Grinlow coral bed. If you go south, due south from the temple, over a couple of ridges, you come to this not slightly, poorly defined ridge with a lot of outcrops on it. And this is actually a layer of coral, not great coral, but still visible coral. And if you have a look along that layer, you can see, and I'll zoom in if I can, you'll see features like this, which are clearly fossils, fossil structures. Another one here, and again, and another one here. And these are what are called colonial corals. Each of these lines here is a corallite, which is preserved in the fossil. And these were colonial corals that lived together and symbiotically in big clusters. And there's a whole load of these along that coral bed. This particular one, those particular one is one called Syringopora. It's a tabulate coral, and better fossils of it, if you extracted them, looked like this, a whole series of colonies joined together. And these would have sat on the seafloor like this, growing quite happily. What we see is all that's left is these hard parts, these calcium carbonate corallites, but the living parts would have been popping out, filter feeding on the seafloor. There are other corals down there. This is another one called Siphonodendron. And this can also be found up there on Grinlow. And you can see the internal structure. It's another colonial coral, lots of corallites living together. There are tabulae, which are these cross sections, and septa, which are these vertical sections in the coral. And I have to admit, if you want to go and see Siphonodendron and a really good coral colony, go up Fairfield Road and about a couple hundred yards from the roundabout. There's the BCA bench, and behind it is a wall, and this is a superb Siphonodendron colony. Okay, it's not on not on Grinlow, but it's certainly worth a quick visit. And if you look at it up closely, the rock is full of corallites of Siphonodendron. And not only can you get these longitudinal sections, in places you can get cross sections of the corals. And if I zoom in, you can see beautifully the scepter here of the corallites. And this was a big colonial coral. And the whole of that wall has these Siphonodendron colonies on them. And it's actually a genus called Siphonodendron juntium. I'm not a paleontologist, but it is one of the few fossils I am familiar with. Back to Grinlow. Other corals up there, they're also what are called solitary corals. So these ones don't work in colonies. These are separated corals, similar sort of structures with septa and tabulae. These are rugose corals, and this one is Dibunophyllum, and you can find that in that coral layer. This is a cross section, not a great one, through one of these solitary corals. If you isolate them, this is what they would look like. You don't get fossils, unfortunately, like this up there. And these would have been not colonies, but groups of these solitary corals growing quite happily on the Grinlow sea floor. There are other fossils up there, not great examples, but still evidence of what it was like back in the Carboniferous. You can probably see these structures in here, lines in here. This is the remains of a sponge, Chaetites, and it's a sponge which has ancestors living today. There's the occasional planospiral, plain spiral gastropod you can find in that coral bed. And of course, the lower Carboniferous is very famous for its crinoids. Round Derbyshire, you can find some wonderful crinoid outcrops. They polish the stones and make very nice ornamental stones. Not so much in up on Grinlow, but if you look closely, you can find the stems of these crinoid stems here, cross sections through them. They are there on nicely weathered surfaces. And so these would have been abundant up there on Grinlow, but not very well represented in the fossil record. Crinoids are members of the starfish family, extinct now, but they were attached to the seafloor. The stems is what we see the fossils of. The tops had fivefold symmetry, which is like starfish, and they used to live on the seafloor and were very abundant during the lower Carboniferous. The other fossil that's quite abundant up on Grinlow, not particularly well preserved, are these shells, which are parts of brachiopods, shellfish called productids, and these looked like this in full, and they used to sit on the sea floor, held together by spines. They had a flat top shell which used to open up and filter feed, and you can see these around on the rock faces up in Grinlow. One also a feature you probably noticed if you walked up there is this kind of feature in the rock. This is called a stylite. This is not fossiliferous at all. It's just a solution layer where the limestone is dissolved under pressure as it was lithified, and the amount of limestone that has disappeared supposedly in these stylites is equivalent to the wave height. But you probably see a lot of stylites up there if you keep your eyes open on Grinlow. If you want to see productids, really good examples, productids, go to the football ground, walk down Holker Road, and there you can find a whole suite of productids in the cutting through the road here. Most of them in this sort of shape, facing upwards, which suggests that they died peacefully in their beds rather than were washed around by some storm. Now, Grinlow, we keep talking about lots of fossils there. Where are all the fossils then? If all we can see is these little bits of fragments. Well, the best way to look at it is to make a thin section of the rock up there. And if you make a thin section, and what we do is we take a slice of rock, cut it right the way down to 30 microns thick. And at that thickness, most minerals, especially rock forming minerals, are transparent. We put them under a polarizing microscope, and the minerals have different optical properties under that microscope, and we can start to see the internal structure of the rock on a microscopic scale. And here it is. And these thin section photographs, and there's 500 microns, so this is about 2 millimeters across this. These are all taken from the Below limestone up on Grinlow, and that dull gray rock suddenly comes to life. This is a section full of fragments of brachiopods, not whole brachiopods, but it's actually full of fragments of brachiopods. It's also got these little creatures here called forams. These were tiny little coiled creatures which were very useful in aging the rocks before they had proper age dating techniques, absolute age dating techniques, because they evolved very quickly, were very well dispersed, died out very quickly. So it was easy to correlate different rocks between them. If you zoom in on some of those brachiopod fragments, this is what you can see. You can see the growth zones of the brachiopod, and you can see where their spines were actually attached to the brachiopod shell. And these are all the growth zones of calcium carbonate of the brachiopod. Other thin sections, lots of brachiopod fragments, some of the spines that formed the brachiopods, that they attach themselves to the mud, green algae, bryozoa, a whole mass of life seen and revealed in the thin sections. Another sample here shows a really nice foram, very famous one found worldwide. Even fragments of quite rare fragments of trilobites, which went extinct at the end of the Permian, just after the Carboniferous. So there were trilobites up there too. And crinoids, probably an awful number of these fragments, broken fragments, are actually crinoid fragments. Occasionally you can see small whole crinoids in these thin sections. And between these fragments is fine-grained material, and this was calcium carbonate mud precipitated in those tropical seas 340 million years ago and cementing the rock together. And overall, the rock on the Below, up in Below, is 98.5% calcium carbonate, which is why they used it for lime burning, because it was so pure, and which is why that they're mining it in quarries around the Peak District. Now, most of Grinlow is the limestone, and here's the temple. Here's the cavern, but there's this pink stuff, and this pink stuff is lava. And into this tropical idyll, there were volcanic eruptions, not big ones, but they would have been like this. And it seems most of them were basalts coming up from the mantle, because at that time, the crust in this area was being slightly pulled apart, allowing molten material to come all the way up from the mantle, and it came out probably beneath the sea, forming lava flows like this. Occasionally, they may have come out on the surface, because there are plenty of very fine-grained materials associated with these lavas, which may have been ash, a bit like the ash that's come out in the Tongan eruptions, but on a much, much smaller scale. So these were basaltic eruptions taking place at the same time as the limestone was being produced. The lava, the lower Millersdale lava, as it's called, that you find up on Grinlow, probably spread out over a whole of this northern part of the White Peak District, right up to Castleton, never more than about 30 meters thick, lots of little individual flows, but significant volcanism. Now, here's the outcrop, and if you're up at the temple, it forms the lava is down. You can follow it down towards the Ashbourne Road. And if you go here, you can find an outcrop of it, but it really is a rock only a mother could love. Dull, grey, darkish rock, covered in lichen and mosses. And if you break it open, it looks like this. It's heavily altered. This brown patch, this used to be a nice olivine crystal, probably clear green olivine crystal, but it's completely altered and oxidized to this brown iron oxide. And a lot of this material in that rock now is clays, clay minerals formed after the weathering and alteration of the basalt. Little white flecks here are probably the mineral feldspar. Now, the lower Carboniferous idyll, which was the so-called Mississippian of the lower Carboniferous, didn't last forever, maybe 20 million years or so. And eventually it got curtailed by what we can now see to the west of Grinlow. And this is the upper Carboniferous rocks, which form Burbage Edge and the Goyt Valley. And these represent big deltas which spread in over this area of limestone and killed off all that wonderful life. And it was due to earth movements, slightly raising of the lands, spreading these deltas from the north, the southeast, and from the west over this area. And they arrived about 326 million years ago. Firstly, you got fine-grained deltaic muds spreading over the area. Then it was followed by major channel sandstones of material being eroded down, and these deltas would have covered the whole of Grinlow and eventually built up to make forests and produce coals. When we look to the west now, what we see from Grinlow is lowland down, which is Burbage. That is where the shales are now to be found. And the uplands, as we go up towards the top of the hill, going out towards Macclesfield, those are thick sandstones, including one called the Roach's Rock. And then on the top, as you probably know, there were coal deposits. And so it's nicely exposed now as a sort of paleo delta. If you want to look at the Bowland Shale, probably the nearest place to go to is Cavendish Golf Course. Those of you know the golf course, just above this is the 10th green. And here you can see a black shale. This was the deltaic muds moving in over the area. And these are quite rich in organic matter, these muds, because they've got material coming down from those forests. When this rock got buried, and it got buried down to 4 or 5 kilometers, the organic matter reached temperatures of 130, 150 degrees, and it turned it first to oil and then to gas. And the rock is so tight, the gas couldn't get out. And so the gas is still in there. And this rock, it's called the Bowland Shale, is identical to the rock that they were going to exploit for fracking up in Lancashire. The delta sandstones, the channel sandstones, best place to go and see those nearby. They're not well exposed on Grinlow. They are very well exposed on the Roaches. If you're in some of these Carboniferous sandstones, you can find good evidence. There were high currents in these channels, making these channel sandstones. You can see the direction of travel of the channel currents and producing these wonderful cross beds. And if you look at the rock close up, it's very gritty with lots of poorly sorted sand grains, making it a grit. And of course, this is the Millstone grit. And if there were quiescent periods, coal forests developed, and that turned to coal between the channel sandstones. And if you want to read about that, read the book by Messrs. Robertson Leach, which is a very good insight into the coal mines that developed on this Carboniferous coal. Now, at this time, there were tectonics going on to our south. The ocean, the Rheic Ocean, was being squeezed, and there was a lot of pressure. And in the end of the Carboniferous, the area got folded. There was also pressure, north-south pressures on the area, which caused and formed the Derbyshire Dome, the anticline that we now see in the Derbyshire area. At this time, this would have been happening well below the surface, and it's only very recently that it's exposed as it is, and of course exposed the limestone that we see now. And if we look to the west, we look up onto Burbage Edge, we see the upper Carboniferous shales and sandstones. So that was after the main rock formation that we see on Grinlow, but it does control the exposures we now see. Now, that wasn't the last event that happened in Grinlow. The next thing I want to talk about is the Grinlow mineral veins. These probably formed in the very late Carboniferous through into the Permian, maybe even through into the Triassic. Nobody's actually really sure of the date of these mineral veins. And Grinlow is part of what is called the South Pennine ore field. I'm sure you're well aware there's been mining in the Pennine ore field for a long period of time, since Roman times. They've been mining lead from 2,500 veins, mostly on the east side of the limestone outcrop. So over towards the east, towards Bakewell, up towards Castleton, down towards Matlock. And these show these traces of all these veins. And they were mining galena for the lead, and more recently barite, barium sulfate, and fluorite for steel making. And the veins also have a lot of vein calcite in them. But you will notice there are no veins marked in the Buxton area, but that's certainly not true. Buxton was part of the Pennine ore field. To the east, you see these lovely veined materials and layers of veins. This is galena, followed by barite, followed by fluorite. These are calcite crystals, and these all show there will be a vein margin here and crystals growing in from the sides of the veins as they were opening. And how these formed was, and these are part of a type of deposit known worldwide, relatively common. Mineralization is never a common thing, but these are relatively common. These are called Mississippi Valley type deposits, and of course you can guess why. And they're formed when fluids from depths, heated fluids, which have dissolved out things like lead, fluorine, barium, calcium. They become slightly acid, probably at temperatures about 130 degrees, because they've come from depths within basins under a big weight of rocks. These are squeezed by hydrostatic pressure up dip until they encounter things like limestones, where there are a lot of cavities. There may be surface water coming down. And of course, the limestone reacts with the acid solutions and causes precipitation of all these elements as the minerals we now see. Now, if in the area of Grinlow, and there's the cavern, there's the temple, there are a series of veins. These in red here were lead veins mined back in the 1700s. Can't see anything of them now. That's all from old records in a couple of very good publications. There were barite veins, big barite veins, which were mined, shown here in green, down by Rock Bay, in the landscaped area on on Grinlow. These were mined for paper and particularly paint fillers sent down to the Goyt Valley paint mill. And all these have gone. But if you go up onto Grinlow, you can still find these veins. The best examples are here, and we'll look at those in just a moment, but also all the way through the woods, you can find old dumps, barite dumps through the woods if you look carefully. Now, the best example is what I call the Cowvane Suite. And this is very near the road, the path up from the car park down by the caravan site. And there's a whole zone here full of veins. And if you look at this area, the whole of this area hasn't been exploited by the lime burners. And that's probably because it's contaminated by these veins. There's a big vein there. There's a little trial where they're probably looking for lead there. There's a fault here that probably helped the fluids come to the surface. If you go up this little track here, it's covered in barite scree. And if you zoom in to that main vein, what you see is chunks of limestone cemented by large crystals of calcite here. Chunks of crystals, you can probably just see the size of some of these crystals. They can be several centimeters long. And if we zoom in, you can see how those crystals have grown out from the chunks of limestone forming this vein and growing in here into an open space. Layers of these are calcite crystals. And also in that face of that suite of veins, you can find multi-veins like this one. This has got carbonate calcite on the outside of the vein, on both outside, and the center of the vein has been filled by the white mineral barite. And in fact, the whole of Grinlow had at some stage fluids pumping through it. Some of them made these big veins, but if you go and look at some of the outcrops, and this is the outcrop near the road down to the car park by the caravan site, about the road to the caravan site, you go and look on some of the joint surfaces, and these would have been fractures which would have controlled fluids rising. You will find on those surfaces barite growing. And if I can just zoom in here, you can see this is a barite crystal that has started growing there and nucleated, forming this lovely rosette of barite, another one just there. And these are all over, once you get your eye in, these are all over Grinlow Hill. If you look at those in section, again, you can see the growth zones in the barite. These are barite crystals growing out, and you can see each pulse of fluid precipitating a bit of crystal. And this represents crystal growth, slow crystal growth from mildly saturated fluids, which leads to very big crystals. And if you go into the woods, and this is an outcrop not far from the cavern, you can find old workings where they dug out material. And if you look at these heaps on either side, these are actually made of barite. And there are a lot of these throughout the wood. And if you look at them closely, these heaps, these are the chunks of barite. There's a lot of orange stuff up in the wood. A lot of that is kind of shaly stuff related to lime burning. But these are little chunks, and you pick them up, they are heavier, feel heavier than your calcium carbonate or the shaly material, because they have a density twice as much. And that's your barite. Now, moving on. By the time the Permian age had come, the UK was now the middle of a continent. It's moving northwards. We're leaving the equator behind. It's very arid because we're in the middle of a continent. We're probably at the line of something like the Sahara today. And if you look to the south, from Grinlow, you'd have seen a giant mountain chain. This was right across Central Europe. This is part of the Variscan orogeny, which was the closure of that ocean called the Rheic Ocean. Yeah, and it was very hot and dry, and these conditions was what would have prevailed over Grinlow. By the Triassic, a few seas had made their way in. It's very hot, very dry, so these are evaporitic, producing the salts of Cheshire. And around Grinlow, there would have been a little bit of life. We'd just had the worst extinction in Earth history, so there wasn't a lot of life around. And the rocks that were being laid down would be the desert or semi-desert sandstones and conglomerates full of clasts like these quartz crystals here. This sample is from near Aldley Edge, and these would have conditions would have prevailed over Grinlow. And then through the Jurassic, we're continuing to move forwards. The UK is beginning to look like the UK. The Atlantic hasn't opened, but seas came and went. And some of these seas would have covered the area over Grinlow into the early Cretaceous. The Atlantic has been in to open. UK again, sometimes it's being submerged, sometimes it's land. The end of the Cretaceous, when the asteroid hit over here in the Gulf of Mexico, we would have been covered by the same seas that produced the chalk to the east. All of these have now been eroded away, right their way down, back down to the Carboniferous. By 20 million years ago, the UK was land being eroded down towards the routes that we now see. But there is one little kick left for Grinlow, and that is what is called a castic infill. There's a dog for scale. If you go through the little gate coming from what I call the sheep field, where all the sheep are, towards and where the cows are, turn slightly oblique right, and you come out to this place with this little low cliff. And if you look closely at this cliff, it's got orange glow on it. And every now and again, you see some of these little sort of orangey deposits. If you look closely, what it is, welded to the Gray Limestone, is this orange material, cemented to the limestone, and also hidden in the grass, because it's quite soft and easily eroded, is material like this, which when you look at it closely, is very gritty. In fact, it looks like sandstone, slightly eroded sandstone with bits in it, chunks in it. And that's exactly what it is. So here you have in our wonderful limestone, some sandstone. So what on earth's that doing there? And sometimes in some of the crevices, and this is one on the way up from the car park towards the trackway, you find the same orange material. If we make a thin section of that material, things become clearer. This is the outline. Again, this is 500 microns. Here's a chunk with a lot of mineral grains in it. And these mineral grains are quartz. Poorly, well, very angular quartz. That means it hasn't traveled very far, but it's part of a pebble made up of quartz crystals. And also there are lots of quartz chunks around here, again, not traveled very far, and they are cemented together by some carbonate. So this material has been put in that castic infill and then cemented by some fluids which precipitated little carbonate cement, probably by dissolution of the limestone. And if we have a look at the chunk of one of those deposits, it looks like this in thin section. It is nothing more than a simple sandstone. And where did it come from? Well, the answer is it's actually Triassic sandstone. I showed you those deposits formed in the Triassic 230 million years ago, and this would have covered the whole of the Carboniferous rocks. It would have sat on top of the Carboniferous rocks. But during the last 20 million years, all those surface rocks have been eroded away slowly down to the level we see. And this was a castic fill. This was a solution cavity in the limestone surface, and it was filled with this eroded Triassic material. In time, it would have been eroded completely away, and there would have been no evidence of it. And it would have, filled completely up with these sandstones, and all we see is the last little bit left. Now, this is known further south in the Peak District. This is the Derbyshire limestone outcrop, and it's part of the Brassington Formation. And the Brassington Formation is a series of castic infills filled with these Triassic sandstones. Some of them are quite thick further south around Bakewell, down towards Bonsall, and then down towards the southwest. As you can see, there's no evidence up here. This is where Grinlow is. And so what these are Triassic sandstones filling the limestones, and we can add the Grinlow outcrops to that Brassington Formation. The Brassington Formation is the youngest rock formation on mainland Britain, found here in Derbyshire and found here on Grinlow. Now, last real event that affected us was the Ice Ages, 400,000 years ago. Where we were would have been covered by the Anglian glaciation, which went all the way down towards southern England. We would have been under hundreds of meters of ice. When that melted, it produced a lot of meltwater, which helped fashion the topography we now see. In the last vestige of the Ice Age, about 18,000 years ago, the ice came down through the Cheshire Gap, but probably didn't quite cover Grinlow. So if you'd looked from Macclesfield towards Shetlandsoe, over towards Axe Edge, you'd have seen a tongue of ice pouring down through Cheshire Gap. But over in our area, we'd have just been tundra, a bit like it was this morning when I was walking my dog. And really, that was the last action on Grinlow, but then the Anthropocene. Then we turned up and started digging up the limestone, digging up the lead, making pipes and bullets, and digging up the barite. So I hope that's given you some sort of insight into the history of Grinlow. Thank you very much for listening.
Wow, thank you very much, Richard. I can't wait now to get back up Grinlow and have a walk in our history. I think I shall see it as well with fresh eyes and perhaps slightly more informed eyes. That was a lot to take in, but so interesting, and I do thank you. Now then, you have a question for some of our audience, I think, just by way of identifying some trees.
Oh, well, I was walking in the woods today and I've been looking, and many of you have seen the same, seen the hair ice phenomenon. It was very good in the wood today, this ice crystals which come out of dead wood pushed out by a fungus. And quite often it occurs on old beech logs, but it also occurs on another type of tree, and that's the tree, if anybody knows, the gate, what up into the sheep field. If you go up right from the cavern, work your way up, you come to a little gate which eventually leads out onto the top, and on the right is a copse with catkins on it, on the trees. What tree is that, please? It's got no leaves on, so I can't tell.
With that, I'm not absolutely sure, Richard, which patch you're talking about, but it could be alder or it could be hazel at the moment. If it's a tree, it's more likely to be alder. If it's a shrub, it'll be hazel.
They're definitely trees. They must have been planted on the heaps above Rock Bay.
Yeah, it's probably alder.
Alder, okay. And
alder,
it has,
or yeah, most likely.
Okay, that sounds good. I shall write that in. I've got to write a little ditty on the hair ice.
But,
So
I mean, alder is used in quite a lot of restoration projects anyway, because it grows and it fixes nitrogen. So it's why it's used in those sort of conditions.
excellent. Thank you.
Thank you, Peter. Now then, has anyone got a question for Richard?
Again, Richard, just a quick question. Presumably, the outcrop below Corber Cross is lower Carboniferous again, is it?
It's upper Carboniferous. I mean, up, yeah. So as you go up to Corber Cross, there are various thick layers of sandstone. They're interbedded by the shale, and you get the Corber. Actually, the one where the punch bowl is called the Corber grit. And then as you go up the hill, certainly to the west, you go through up to the Roaches grit, the one which forms the Roaches, and it's a thick unit. And there's also the Chatsworth grit. These, of course, covered the whole of this area, and in the past, before the folding and erosion, those would have joined up over the whole area. But you're right, up at Corber, that's the thick sandstone, and probably above. Sorry,
same as the Roaches, basically.
Same, yeah. The Roaches grit. If you're going up towards Burbage Edge, you walk over the Roaches grit. Exactly the same rock.
Yeah. And presumably that's what underlies most of Coombs Moss.
Yes, yeah, that will be under there, layers of the sandstone. Which one actually goes right across out towards Coombs? I'm not sure which one is right at the top, but you're quite right. Yeah, it underlies the whole top.
Richard, can you hear me?
I can.
Yes. Can you explain what rare earths are and why we haven't got any or very many of them in this country?
The one thing is that rare earths are actually not rare. It's just a name for them. They occur quite widely. They're often associated with granitic rocks. And if you go and look at our granites down in Cornwall and so on, they do have rare earths. They're in a form in the UK where they're rather dispersed, so very low grade, and in a form that would be very expensive to extract. 60% of the world's rare earths come from one deposit in China, where there's a freak of geology over actually 200 million years, brought up rare concentrations of rare earths into one point. And it's a giant open cast pit, very, very rich in so-called rare earths. And of course, they're very high grade, easy to extract. And so the Chinese control the market. There's been a lot of effort around the world to find other sources, and there are other sources in America, in Europe, and so on. But the Chinese, because they can produce them so cheaply, can make it unviable for other mines to develop, which means they continue to control the market. And maybe that's a kind of dangerous place to be. The UK has lots of wonderful geology, has a little bit of everything. And apart from tin and lead, which we've now mined out, not a lot of most things.
I think, but what are rare earths? I mean, what can you, have they got a chemical?
They're elements. So they're a group of elements, rare earths, which are very good useful in electronics mainly.
Right.
They have very good electronic properties, and they can be used in everything from semiconductors and a whole series of devices. They're just a suite of elements, and they get concentrated in geological processes, often metamorphic and magmatic processes. As I say, they're here in all rocks. You'll find them in all rocks. You just as with any mineralization, you need some suite of circumstances to concentrate them to make them economic. It's the same with the lead in the Peak District. You've got what you had was a source of lead, a mechanism to transport the lead, and then somewhere to precipitate the lead in one place. If you don't have all those, you don't get an ore deposit. And it's the same with rare earths. There are lots of rare earths around. You just need processes, and the processes to concentrate rare earths are rather rare. And as I say, this freak of geology has blessed China with this two suites of rare earths, 200 million years apart. You've got this big concentration of rare earths in this one place, probably relating to what was happening in the mantle below.
Right. Thank you very much.
Thank you, Andy. Anyone else? Yes, Jill.
I'm fascinated by the Avalonia Plate. What caused it to move in the direction that it did? Is it still going strong in that direction? Did it override something that was at Grinlow when it was in Antarctica, or did it push it out of the way?
So it's believed, of course, as you go back in time, things become less clear. And the first evidence that there was this plate was about 600 million years ago. It was a little plate that had broken off a large continent, which was formed down around the South Pole at that time. And these would just be stresses on the Earth, which caused bits of the Earth to fragment. And this was quite a small fragment. So behind it, you would have had an ocean which was beginning to grow. You'd have seafloor spreading, pushing it northwards. And the plates generally, all the plates were just moving in that way, probably floating to a certain extent on the mantle. And there's no reason why it continued to go north. It could have stopped and gone east or west, but mainly the drift of the continents were being driven that way, oceans forming behind it, pushing it further north. And of course, when it collided with the plate that had Proto-Scotland on it, it welded together to form a much bigger plate, this one called Laurentia. And that was just before the Carboniferous. And then that plate moved on further north, carried on further north, but then it split. When the Atlantic started to open, we went one way in America and Greenland went another way. And that's just plate tectonics. I've seen predictions that we will continue to sort of go a little bit further north, and we are slightly moving north, although we're moving away from America, so we're also moving east, and that we will swing round towards where northern Russia is. But don't worry, we're talking 200 million years.
Thank you very much. That's great.
Don't panic.
Not yet.
Well,
I have a question.
oh yes, please.
I'm intrigued about the Blue John, which I believe is the only place in the entire world that it's formed. And I wondered what were the particular conditions which would make this very special mineral be deposited. And does Richard really think it is the only place in the world where it would be? And why would that be?
Right, Blue John is the mineral fluorite, which is calcium fluoride, CaF2. It is not a rare mineral. You find it often, and in these same types of deposits in the States, you can find it. It can occur in igneous settings as well. So itself is quite a common mineral. What you get around Castleton is nice, slow forming conditions which deposit these layers of fluorite, some of which are slightly yellow, some of which are slightly purple. And that gives you your bleu jaune, your Blue John. And it was just those right conditions that produced that particular variety of fluorite. Fluorite, if you go to the North Pennines, you can find lovely purple fluorite. A lot of it is absolutely clear or even a pale green color. And this depends on trace elements. It also depends on the structure of the fluorite and how the light goes through it. And it just seems in Castleton, you had the right conditions. You do get Blue John elsewhere, but it's not as good, so the people in Castleton tell me, as you find elsewhere. And they've got better marketing. I always look at Blue John and think fluorite's actually quite a soft mineral, not a mineral that you would really want in a ring, but it is easy to work. And yeah, there's a very good marketing going on in Castleton, and it is certainly semi-unique and certainly the best advertised place you find it in the world.
Good question, Sandra. Thank you. Anyone else?
And with that in mind, the black diamond, which was found at Grinlow, do we know what that is?
I think they're quartz crystals covered in well, maybe an iron oxide, possibly organic, but most likely to be iron oxide. When I looked at the thin sections, even of the limestone on Grinlow, in it were lots of crystals of quartz, what called bipyramidal. So they basically terminated both ways, nice crystals. These were very small, and it seems that the ones out in the Buxton diamonds were of that type. I must admit, I've never been out there looking for them. You can get bipyramidal quartzes growing in veins. If you've got enough space and fluid going through, you will get nice quartz crystals, and you can get some of these quartz crystals which grow with two terminations. And I think those were the Buxton diamonds. I suspect they're now covered with spoil relating to the health and safety now.
So they're not worth anything. Okay, thank you.
I wouldn't say they weren't worth nothing, but not as much as normal diamonds, no.
Thank you very much. That's great.
Thank you. Well, are we at the end of our evening? Oh, I'm sorry. Andy, go ahead.
I'm sitting here about 100 yards from the resurgence of the River Wye, and I know it's in Poole's Cavern. Have we any indications from the geology of a possible path that it takes between here and there and beyond?
Yeah, there's some people who I know who've worked very much on that, and they'll be much better to answer your question than me. All I do know is it comes from the cavern. I live on the bit of Temple Road that turns up towards the cavern. I believe it goes right underneath where I'm sitting now, and then out towards Wye Head. How it actually goes, I don't know if anybody's actually looked and traced it. I've asked the same question. You can draw a line between the two, but geology is not that straight usually. I know it goes beneath here, but where it goes to afterwards, I don't know.
The fact that it comes out where it does, is that because of any underlying geology? Does it hit a different strata?
Yes, it is. Yeah, I mean, as you go down the hill, you go through the limestones, and eventually you come to the underlying mudstones, and they are impermeable. So that will form a good place for the spring to occur. Yeah.
Good.
Okay. Well, if there's no more questions for Richard, can I thank you all for coming?
Thank you.
I hope you enjoyed what's been another fascinating presentation by BCA.
Thank you very much.
Thank you.
Thank you, Richard. Good.
Thank you.
Thank you.
Thank you.
You're welcome.
Thank you
You're
so
welcome.
much. Good night.
Thank you very much, Richard. That was
Okay. Yeah.
Thank you, Richard. Mike, is it worth mentioning that the second talk in the series is with Dr. Catherine Parker Heath and
Oh, good.
her husband, and they'll be talking about the first sort of human encroachment onto.
Yeah, well, just forgive me, Simon, what's the date of that? It is next month.
It's the 17th of February, I believe, the third Thursday.
17th.
February.
Yeah.
So if you'd like an invitation, Simon will provide you with one. Okay?
Yep. Yep.
All right. Well, good night, everybody, and thank you very much.
Thank
Bye-bye.
you. Good night.
Good night.
Good night.
Bye. Thanks, Richard. That was brilliant.
Yeah, thank you, Richard. Excellent.
yeah.
You're welcome, gentlemen. Yes.
I said that Peter would have the answer for you.
Yeah, you are. Thank you. Yeah.
Well,
no,
I without seeing the tree, I may have misled you, of course, but that's my best guess.
it sounds consistent. Next time you're up there, and it's that little gate that there's a slightly narrow.
Yeah, the one that connects back through to the caravan park eventually.
Eventually, I mean, it's on the west side of the quarry. That
Yeah.